And now to finish off this part of geometric probability, we're going to talk about complements. And I don't mean complimenting how you look. Complement actually comes from the word complete. If you ever heard the phrase, ooh, that complements your outfit, it means it completes the outfit, it fits in and fills in what was missing. So that means that an event and its complement represent the complete set of outcomes, or 100%. So we get this equation. Probability of the event plus probability of the complement is 1, or 100%, depending if you're doing decimal or percentage notation. You can write the complement as not the event. The complement is sometimes shorted as E to C. It can even be E prime. We've used that for complement before. So this leads to the abbreviated equation. Probability of the event plus probability of its complement is 1. So in this example, which is from an early one, we're going to calculate the probability of not landing in the semicircle to the nearest hundredth. Well, I already calculated the probability of landing in the semicircle was 0.39, or 39 hundredths. And I know that the probability of landing in the semicircle and not landing in the semicircle must equal 1. I'm going to substitute in the 39 hundredths and then subtract it from both sides. And that tells me the probability of not landing in the semicircle is 0.61, or 61 hundredths. So all we did is we made sure that both probabilities add up to 1, and then we solve for our unknown. For the spinner problem, I'm going to calculate the probability of not landing in section A, or the complement of A. Again, I remember that the probability of A, we already calculated that, was 1/3. So I'm going to say that probability plus probability of the complement is 1, substitute in, subtract 1/3 from both sides. So 1 minus 1/3 is 2/3. So the probability of the complement of not landing in A is 2/3. Now I'm going to do a different example with a traffic signal at A.W. Grimes and Gattis School Road. So this is for cars, and we're going to imagine that it has 20 seconds of green, 62 seconds of red, and 3 seconds of yellow. What is the probability that the light will not be red when you get to the intersection? Well, we still have to find the total time, which is 20 plus 62 plus 3. And what I'm going to do, there are a couple ways to do it. I could just add up everything that's not red and make a ratio from it, but I'm going to use the complement. So I'll find the probability it is red. So that would be 62 over the total, which is 85. And as a decimal, that's about 0.73, or 73 hundredths. So the probability it won't be red, that has to add to the 73 hundredths to be 1. Subtract 73 hundredths from both sides, and I get 27 hundredths. So there's a 27% probability that the light will not be red when you get to the intersection. So why must the probability of an event and its complement add up to 100%? Well, complete, shouldn't that be everything? That should be 100%.